In this online lecture, we are going to learn about how to solve questions on enthalpy. Last time we studied about what is enthalpy change, and what is molar enthalpy. And now we will be learning how to solve the questions based on enthalpy change. Now, before we begin, we want to discuss a formula here. So we last time we learned that molar enthalpy change delta HR, which is associated with 1 mole of the substance. Okay, and now what if you're asked on the question that the substance is not 1 mole, it is other than 1 mole, it can be less or it can be higher than that. So what would you do in that case? In that case, you will find the number of the amount of substance N and multiply it with the molar enthalpy change. Okay, so this is the molar enthalpy change. It is this enthalpy change is associated with 1 mole of substance, and the number of moles that are given in the question, you will multiply it with them, and then you will be able to calculate the total enthalpy change, okay, for that substance. So this is a new formula, you can say, to calculate for the enthalpy change for substances which are other than 1 mole. So I will write which are other than 1 mole. So this is molar enthalpy change. This is the amount of substance. And this is the molar enthalpy change delta H for 1 mole of substance. Now let's go ahead and read the question. What does the question say? If 1 gram of sample of ethanol is spread across the skin and evaporated, what is the expected enthalpy change? The molar enthalpy of vaporization of ethanol is this. Now what is given in the question is we have to find enthalpy change for 1 gram of substance. It is not 1 mole. So we will be using this formula. Now we will go ahead and first of all write what is given information in this question. So the given is this thing, the mass of the ethanol. Okay, I will write ETH, mass of ethanol, which is 1 grams. And then next thing what is given is enthalpy of vaporization. So this is molar enthalpy. This is for 1 mole of ethanol. So I will just write delta H vaporization. So this R can be replaced depending upon the type of reaction. This we did last time. We showed you so many examples also. Delta H vaporization is equal to 38.6, right? We can write kilojoules per mole. And then what we need to find, so what is required in this question is delta H. So let's go ahead and use this formula here. Delta H is equal to N times delta HR, right? So what is N now? Let's find N. So N is the number of moles. So how do we find the number of moles? We divide the given mass by its molecular mass, right? So mass of ethanol divided by its molecular mass. So what is the mass of the ethanol that's given? It's 1 grams. And then what is the molecular mass? How do we find that? So molecular mass for ethanol is CH3, CH2, OH, right? So carbon weighs 12, 3 hydrogens will weigh 3, this carbon will weigh 12, this will weigh 2, this will weigh 16. What is the weight of this one? It's 1. So you go ahead and add them. So if you want to take the zeros also, like 1.01 is the mass, like that. So what you will find is up to some decimal points. I've just given you a rough idea. So what's the along with the decimals, the value of the molecular mass for ethanol is 46.08 grams per mole. Okay, so I'll go ahead and use this molecular mass here. So 46.08. So when you go ahead and do the calculations, I'm going to erase this now. So 1 divided by 46.08. So let's put it in the calculator and find the number of moles. So the number of moles will be equal to 0.021701. Okay, so this is the answer we are getting now. Let's go ahead and use this formula here. So delta H we want to find, N is 0.021701, and then times, this is 1 here, and times the delta H vaporization, right, which is 38.6 here. So let's multiply these two numbers, put it in the calculator, and what would be the answer here? It would be 0.838. 0.838. Okay, and delta H will be in kilojoules, right? And if you want to play around with the decimal and this kilo here, so this will be 10 to the power minus 3, this will be 10 to the power 3. So what will be the answer in joules? It will be 838 joules, right? Now let's go ahead and try to solve the next question here. Okay, so in this question, what we are given is, let's go ahead and read first. A student places 125 gram of liquid water at 24.2 degrees Celsius into a calorimeter and then adds 10.5 grams of solid potassium bromide also at 24.2 degrees Celsius. And then he what do? Does what? He stirs the liquid until the KBr dissolves and then determines that the temperature has changed to this much, 21.1 degrees Celsius. What we have to calculate is the molar enthalpy change for this dissolution reaction. Okay, now let's go ahead and first pen down what's given information. So given is the mass of water. Okay, so the mass of water is, I will write MH2O, it's 125 grams, and then what else is given? T initial, so initial temperature is 24.2 degrees Celsius, and then what happens, and then he adds 10.5 grams of KBr, and next is given the mass of KBr. Let's go ahead and write that 10.5 grams, and then what he does, he dissolves that and then he give it a stir. What happens? The final temperature is TF is 21.1 degrees Celsius. It changes to 21.1 degrees Celsius. What do we need to find? The molar enthalpy change, right? So let's go ahead and find that. Just first write what is required. Molar enthalpy change, because this is a dissolution reaction. Okay, so I will just write here, or it is a solution reaction, it involves solution, so we need to find this. So what we will do, because we know that the enthalpy change is equal to the heat that is exchanged during the reaction, right? So let's go ahead and find the heat of the surroundings, which is Q. Okay, so Q is equal to mc delta T, right? And in this case, Q will be Q of the surroundings. Okay, so let's find out what's the heat of surroundings. Q surrounding is equal to mc delta T. I will just tell you more about why we wrote surroundings here. So what is M here? That would be water. So what he is doing, the student is placing liquid water at 24.1 degrees Celsius into a calorimeter. So let's say this is your calorimeter, and then he places some water here, and then he is adding the KBr into it. Okay, so what he's saying, that what is the molar enthalpy change for this dissolution reaction? So because water is your surrounding here, so that's why we are writing here surrounding. Q surrounding would be equal to mc delta T. Here you will take the mass of water, so I'm going to write here MH2O, the specific heat of water, and the change in temperature that is related to the water, right? So let's write here, instead of delta T, it will be better to write T F minus Ti, right? So what is the mass of water? It's 125 grams. So let's go ahead and write that. And then what do have I have the specific heat value for water. We already know it's 4.18. And what is the initial temperature? Sorry, final temperature here. So the final temperature was 21.1 degree. Okay, and what is the initial temperature? 24.2. Okay, so let's put these numbers in the calculator. We will have this thing Q surrounding. So from here you will get the negative number. So it would be minus 1.620 into 10 to the power 3. Okay, joules. So this is your answer. This is the Q for surroundings, that is of water. Okay, I will just write surroundings here. And then now we are to find the enthalpy change for the system. So delta H for the system would be, so what is happening here? The initial temperature was 24.1 and then the final temperature was 21.1 degrees Celsius. So since the final temperature is lower than the initial temperature, the surroundings lose thermal energy to the system. Okay. So what happened? The temperature of water dropped. So surroundings lost the temperature. Okay. That means system is absorbing that. Okay. So therefore the system, so delta H system would be a positive number. So it would be 1.620. So you already know from this, from a previous online lecture, Q surroundings is equal to negative Q system, right? So when you'll put this number here, the negative and negative sign will cancel, so the delta H system will be 1.620 into 10 to the power 3 joules. Okay, so this is your enthalpy that is related to system. Now what do we need to do? He is asking about molar enthalpy change if you read the question. So how do we find that? So for that, first of all, let's find the moles here. What are the number of moles that are involved here? So the number of moles. So to convert this enthalpy into molar enthalpy change, we are finding this number of moles because we want to use this formula. Delta H is equal to N into delta HR. Okay, and we want to find this delta HR here. Okay, so we will rearrange this equation. Delta HR is equal to delta H upon N. Okay, so this we will use here. So we need to find this N. So what that is what we are doing here. So N, the number of moles, is the mass. So mass of the system, your system is KBr here. So mass of the system divided by its molecular mass. Okay, so what is the mass given here for KBr? It's 10.5. Let's go ahead and write that, and then divide by its molecular mass. So if you go ahead and calculate the molecular mass of KBr by adding the mass of atomic mass of potassium and atomic mass of bromine, so you'll end up having 119 as your number. So let's write it down here. The number of moles is equal to the molecular mass. Sorry, the mass of KBr upon the molecular mass of KBr. So the mass given is, just one second, the mass for KBr was 10.5 grams. And then what is the molecular mass? I just told you 119. So if you go ahead and put it in the calculator, you will get 0.08. So maybe we just write this much here, 0.08. I think it is double eight. Okay, 0.088. Okay, and then let's find the delta H value, the molar. So I already told you we are going to use this formula here, and then we need to find delta HR. So we will rearrange this equation. Delta HR is equal to delta H upon N. Okay, so what is the delta H? We just calculated like before this step. The answer was 1.602 into 10 to the power 3 divide by 0.088, right? So let's go ahead and put these numbers and find the molar enthalpy change. So the number will be 18 kilojoules per mole. So this is your answer. Now, after this, we will be studying potential energy diagram changes for, let me clear this first. Potential energy diagrams for exothermic. So for here, we will write potential energy diagram for exothermic reaction, and here we will draw potential energy diagram during an endothermic reaction. Okay, so let's see here, and then we'll proceed to the next topic. So what we have here is this thing. So this is on this axis you have reaction progress. Okay, so with time how the reaction is progressing, and then over here you have potential energy on this axis. So for example, water gas, we have the gaseous form of water as your reactant, and then what is happening here? Sorry, we are having this thing here. The condensation reaction of 1 mole of water vapor is exothermic. So condensation means it is going from the gaseous state towards the liquid state. So the reactants are at high energy. Okay, so we will write this H2O gas here, and then what will happen? It will release energy to the surroundings, and these are the products, water, liquid, right? And what is the delta H? That is enthalpy change that is involved here. So delta H condensation, I will write it because this is a condensation reaction, and it is minus 44 kilojoules. So you already know this. Energy is released to the surroundings, and if you go ahead and plot this one here, and the vaporization reaction of liquid water. So this is your, let's say, the A diagram. This is your B diagram, the vaporization reaction. So what is happening here for the vaporization? Because this is an endothermic reaction, it will require to make liquid water. To turn it into gas you need energy. So this is these reactants are at lower energy level initially, and then what is happening? So the water in gaseous form, it will be formed when you give energy from the outside. Okay, so they take energy from the surroundings. So the delta H vaporization, I will write it because this is vaporization reaction, it is plus 44 kilojoules. So I hope you understand the signs as well, and where's the flow of energy here, and what is the level of reactants and products in different reactions. So on this axis you already know this is reaction progress, and on this axis you have potential energy. Now let's go ahead and do one more question. There are some different type of questions. Okay, so let's first write the question down, and then we will try to solve it.